Milligan's experiment, determination of charge. Milligan's experiment is used for the measurement of the charge of an electron. Principle. The method is based on the study of the motion of charged oil drops under free fall due to gravity and in a uniform electric field. By adjusting the electric field suitably, a given charged oil drop can be made to move up or down or even kept balanced in the field of a view for a sufficiently long time, and a series of observations can be made. Experimental arrangement. The apparatus consists of two horizontal circular metal plates A and B, about 22 centimeters in diameter and spreaded by a distance about 16 mm, which is given in figure 7.6. The upper plate has a hole H in the middle. The plate are surrounded by a constant temperature bath D and the chamber C containing dry air. The plates are connected to a potential difference of the order of 1000 volts. Theory. By means of an atomizer, a spray of a fine droplets of a highly viscous liquid such as a glycerin is produced near the hole H is the upper plate. The droplets move down slowly and pass through the hole H and enter the space between A and B. The droplets are illuminated by an R lamp capital L and are seen through a microscope M whose eyepiece is provided with a micrometer scale. One such droplet is viewed through the microscope as it descends under gravity. The viscous drag on it due to air increases and soon it attains a constant terminal velocity. The terminal velocity of the droplet is measured using the microscope. In general, Milligan's experiment are under three cases: motion under gravity, motion under electric field, mass of an electron. Let me see first part, motion under gravity. The gravitational force acting on the oil drop downwards is equal to mg equal to 4 by 3 pi a power cube rho into g, where a is the radius of the oil drop, rho is the density of the oil, and g is the acceleration due to gravity. The drop displaces air of volume 4 by 3 pi into a cube. Weight of air displaced by the oil drop 4 by 3 into pi into a cube into rho into g, where rho is the density of the air. The net downward forces acting on the oil drop equal to weight of the oil drop minus weight of air displaced by the oil drop equal to 4 by 3 pi into a power cube into rho into g minus 4 by 3 pi into a power 3 into rho into g equal to 4 by 3 into pi into a power 3 into rho minus sigma into g. Since the oil drop attains a terminal velocity, the net downward force acting on the oil drop is equal to the viscous force. By Stokes' law, the viscous force on the oil drop is 6 into pi into eta into a into v, where eta is the coefficient of viscosity of air, 4 by 3 pi a cube into rho minus sigma into z equal to 6 into pi into rho into a into v. Equation 1. The radius of the oil drop, since a equal to 9 divided by 2 into eta into v divided by rho minus sigma into z, the whole power of equation 2. Motion under the electric field. The air inside the parallel plate is ionized by sending a beam of X-rays. The droplets pick up one or more electrons from the ionized air. Let Q be the charge carried by the droplet. Under observation, let an electric field capital E be the applied between the plates capital A and capital B, so that the drop moves upwards with the terminal velocity v1, which can be determined using the microscope. The force on the droplet due to electric field is equation. Since the velocity of the droplet is uniform, we have equation minus 4 by 3 into pi into a cube into rho minus sigma into z equal to 6 pi eta into a into v1, equation 3. Adding equation 1 and 3, we get equation equal to 6 into pi into eta into v plus v1 into a, equation 4. Substituting the value of a in equation 4 from the equation 2, equation equal to 6 into pi into eta power 1 by 2 into v1 plus v2 into 9 divided by 2 into v divided by rho minus sigma into g, the whole power 1 by 2, equation 5. If V is the potential difference in volts between capital A and capital B and D, the distance between them in meters, then capital E equal to capital V divided by capital D. Milligan determined the value of Q for a large number of oil drops using equation 5 and found that an integral multiple of a least value, the greatest common factor gives the charge of E into of the electron. The charge of an electron was found to be 1.602 into 10 power minus 19 coulomb. Mass of the electron. From the values of E divided by m and E of the electron, the mass of an electron can be calculated. Mass of the electron capital M equal to charge divided by specific charge equal to E divided by small e divided by M equal to 1.602 into 10 power minus 19 divided by 1.759 into 10 power 11 equal to 9.11 into 10 power minus 31 kg. Thank you.